we present generalizing dataset distillation via deep generative prior, a new method of distilling more generalizable datasets by optimizing in the latent space of a generative model. Given a dataset of real images, we perform generative latent distillation, wherein we optimize a set of latent codes such that when these latent codes are fed through a generative model, we obtain a set of distilled images. These images can then be used to train a network from scratch, such that this network will achieve similar test performance to a network trained on the real data. These images are visually much smoother than those distilled in pixel space, and empirically generalize much better to unseen architectures. Given a dataset of real images, the original task of dataset distillation concerns the synthesis of a much smaller dataset of synthetic images, such that when training a network from scratch, a network trained on this small synthetic dataset will have similar test performance to a network trained on the full, real dataset. Distilled datasets perform well when used to train the same network architecture that was used during the distillation process. However, these images are actually overfit to this baseline architecture, as evidenced visually by high-frequency patterns and empirically by a drop in performance when training unseen architectures. To combat this overfitting, we propose GLAD, or Generative Latent Distillation. Given a dataset of real images, we optimize a set of latent codes rather than pixels. When these latent codes are fed through a generative model, we obtain a much more generalizable set of synthetic images. When training a network from scratch on these synthetic images, we achieve similar test performance not only on the baseline architecture, but also on as of yet unseen architectures. GLAD acts as a plug-and-play module that can be added to any gradient-based dataset distillation method, such as trajectory matching, gradient matching, and distribution matching. GLAD shows remarkable improvements in cross-architecture generalization across many datasets for trajectory matching, gradient matching, and distribution matching. Visually, we can see that the depth of our latent space significantly affects the strength of our imposed generative prior. Our best results come when we choose an intermediate latent space that strikes a balance between realism and expressivity. While we typically initialize our latent space with a feed-forward pass through the generator, we can replace the feature maps with random noise to obtain a mosaic effect that can persist into the final images depending on the chosen latent space. While our standard generator is a StyleGAN XL trained on ImageNet, our method remains fully functional when using GANs trained on other datasets, such as FFHQ or Pokemon, or even GANs left at their random initialization. While we can see artifacts left over from the GAN's original dataset, these GLAD images still all outperform images distilled in pixel space. We'll now conclude with a brief gallery of some of our distilled images. Thanks for watching, and please check out our poster session or website to learn more.